It's Moritz Mungenast, founder of 3F Studio, which is going to be my first question. What is 3F Studio? He actually was part of the building envelope chair at TU Munich, is still in process of finishing his PhD in that field, and initiated the TU group Additive Manufacturing and Construction. Second one is being prepared. It's not you, it's the other one. So that's Moritz, which actually came in perfectly in time, so I just introduced you. And then there's Oliver Tessin, which we still hear to be finally fixed. Also TU Munich student, did his master thesis there, and I like this quote in his CV. Bastian, how long do I need to talk? Another 30 seconds? 20 seconds? Okay. Create concepts that fuse form and function. Ooh, that's an interesting. A form follows functions. Huh? This is what we are very much used to, and now we are fusing form and function in one thing. Maybe you start talking so that we say bridge the time. 3F Studio. What is 3F Studio?
Fused form and function.
Ah, here we go. I'm not. Okay, they had that 20 seconds. Well, you start with that one. That's a good one. Thank you.
Thank you very much for the invitation. We're splitting this lecture in two parts. One is the part starting, or I'm telling the story from a research project, which went then into the first application. And the second part will Oliver take over and present his works with the Studio Tessin. So, okay, now it's working. So we'll take you to the research project called 3D printed envelopes I invented at the Technical University in Munich. And then I will talk about 3F Studio, our projects, and the first application at the Deutsche Museum, and our status quo of prototyping and certification. And then Oliver will take over with approach and methods of our work, and then we'll move over to the Studio Tessin with the different topics. So 3D printed envelope, this was done by me at the chair of architectural design and building envelope. It's a really small chair at the Technical University of Munich at the architectural faculty. And this was run by Tina Wolf as a professor, and her topic was the energy capture of facade systems. And then since 2014, my colleague Philipp Molter and myself were running this chair. His topic is on adaptive auto-reactive facades, and my part is the 3D printing envelopes. So the research really started with the idea that we're somehow entering a new era in architecture with computer-based design and generating complex geometries through parametric design as well, being able to create really complex geometries. And then eventually, after finding out, okay, that's really hard or not even possible to produce those geometries, we have the opportunity now with additive manufacturing really to produce them in scale 1-to-1 even. And my motivation was really to find a meaningful application for 3D printing in architecture, because there are some approaches we of course need, but I was always really interested in the application. And so besides all the different advantages of 3D printing, like individualization, complexity, topology optimization, I really focus on the functional integration of this topic. And the facade hereby really plays like a really good showcase, because there are many functions on a really tight space. As you can see here, there are different functions like sun shading, insulation, ventilation, structural behavior. Now it's working again. And it's always, the facade is really a building component which shows the actual state of the art and the new technologies, if you look at the architectural history. And the hypothesis, I did like a doctoral thesis on this topic, is like that we can achieve the same performance with a 3D printed functional integrated building skin by reducing the technical devices in the facades. Because right now there are more and more technical devices like electric engines, sensors, and so on. And this facade becomes a really high-tech piece, building component. And we were always looking into like how we can reduce all these technical components and make it like a low-tech facade again, which still has the same performance. And the topic of functional geometries was the first one, which was like the problem in the beginning to find out which facade functions can be 3D printed. So it can't be all the facade functions, but which ones. And I'm just going to show two examples. Here, for example, a multifunctional wall component. I did some teaching on this topic then with students. For example, this is from Bruno Kinchala, a project where we always were looking into biological references and then transformed them into, or biological reference with like similar functions, and then transferred them into like geometries which we could parametrically control then. As you can see here, it's different channel systems where you can change the thickness of the wall of the channel and or the diameter inside and outside. And this led then to like a functional wall where you can imagine putting different elements through, like air and water, and even having like a really reduced surface area and having high stabilities and even like properties of insulation. And then we transformed it really into a 3D printed object to really show that it's really possible to print this element. And here you can see just an example where it could be located as a load-bearing wall of a building, for example. Another topic is the moving components. This was done with a student, Yves Teresov, where we were looking into parts of movement at the facade. This is always quite interesting and important. And there the biological reference was the Venus flytrap, which can open and close itself. First, there was this analytic approach of the movement, and then it was transferred into a piece where we can really get this moving going with a pre-tensioning geometry. And in this case, we used air pressure to get the movement, but it would be possible to integrate some material, which like a phase-changing material, for example, to get this movement going automatically when the temperature is getting higher or lower. And there we reached a degree of 90 degrees at the end by optimizing the geometry again. And as an example, it could be like a facade which, like when it's hot, it's opening up, and when it's cooler, then it's closing down again. And as a next step after this first year of doing this research on functional geometries, we started like a bigger project where we tried to functionally integrate different functions in one big element. And out of this came fluid morphology. This was done with Oliver in the teaching team and for great students who made this project work. And there was the goal really to get a one-to-one scale prototype going for the solar station at the TU Munich. We have this solar station on the rooftop where we can test one-to-one facade elements, as you can see here in the middle. And this space behind is separated, so we can make like some comparison measurements, which are just showing potentials. And there the topic was this surface of, and morphology of a surface geometry to create different foldings. And we started this design approach with different layers. And in this point, we or divided them in different scales, like a macro layer. This layer really gets adapted to the different usages inside the building or outside in an urban scale. And as a meso surface, we designed the shading surface, where we create this wave geometry, especially for the certain location and orientation, to keep out the summer sun angle, which is really high, and to let in the lower sun angle into the building in the winter months. As the third layer, the micro layer, it's an acoustic layer where we can inform this surface according to inner and outer acoustic pollution, let's say. So the sound gets not reflected directly, so it gets spread out, and this will have an effect on the acoustic quality. And those three scales or layers fuse together to one design layer. So all those function and form the outside surface of this element. And then we have the inner life of this element as well, the insulation layer, which is in the same time structurally active. So it's a cell structure where air gets locked in and is used as an insulation material, let's say. And as a third function, we have the integration of ventilation channels. You can see the little channels there. So they get integrated in this panel as well. And there we have the possibility of preheat, to preheat the outside air, which gets lent through this channel to the inside. And by staying a little longer in the inside of this facade panel, it gets preheated until it reaches the inside of the room. And those further functions then create the final facade panel. We designed this with the students like in a really small team, like a little office, where we, in a period of 3 months, got to this final stage of this design. And as the next step, we created the prototype. So this was really the first 3D printed translucent and multifunctional facade element. And here you can see the positioning, and we produced it with a delta tower in the basement of the TU München, 6 pieces, which got stuck together into an aluminum frame. As you can see here, it's 280 by 160, and then we installed it last year in March on the solar station to really make this long-term monitoring about like how is it behaving with cold and heat, and to check out the architectural quality of the inside. As you can see here, the shading parts and the more translucent parts. And it worked out that the shading geometry really had an effect compared to the normal facade element by 2 to 3 degrees Celsius. And this really gave us the, let's say, the power to go further with this project. We got a lot of visibility from different newspapers, design, architectural blogs, and got onto television as well. And for this, we thought, okay, we have to team up and try this out to put this into the real world. And so we created 3F Studio, like a studio for innovative 3D printed architecture. And this is now run by 3 founders. So besides Oliver, it's also Luc Moroni, which is here as well. And Trent now, Hoon is starting with us for our marketing strategies as well. And just to see our backgrounds here as well, like I'm more from the facade research and development side. Oliver is doing complex geometries and research, and Luc, he's our, we call him the 3D printer whisperer, from a digital design to production, he really knows how the printer works, and then we can feed back this information into our design process. So we're 3 architects, but with like really different expertise. And yeah, talking about expertise, we have some expert networks around us on facade engineering, material scientists, all the testing facilities, and so on, finance, legal stuff. And what really moves us is really the problem of the end of materials, that somehow we have to find new materials to get our, I think, big topics in the building industry going for the next couple of decades, let's say. And we're looking into using like recycled material at the moment, PET bottles, for example. So we'd already printed with this material, but in the future we're really looking into bio-based material plastics, transparent plastics like chitin and algae, where there are already some materials going. So we're pretty sure in a couple of years that we can print out of these materials facades. And of course the problem plastic pollution, we are targeting there really a closed material cycle where we produce 3D produce facades, and then after their usage we can shredder them, making new material and using them 100%. So with the material PET, that's already possible for the bottles. They can be refabricated in 100% 7 times. And I was talking to our material manufacturer in the moment. There are like 3 to 4 circles possible without putting any new material into the circle. So compared to standard building materials, it's really like a really important step. Besides, like for the primary structure, I always believe into wood, of course, but I think here for the transparent and translucent elements, we have to find new ways. And of course, building process, everybody knows it. We're just getting there to a much more efficient way to produce building components. Our vision is to reinvent architecture through intelligent design with this fascinating technology where we're all here, and fully recyclable materials. So at the moment you can see, just as a first application, the facade where you have many different materials, a lot of production steps, a lot of possibilities of failure, and of course you don't have the closed circle of material. And there we put our solution against by really simplifying the planning process and especially the fabrication process. So the first applications where we see it is exterior, like really facades, like museums, concert halls, and so on. And this is like the first step because we're still working in a translucent spectrum. And then, of course, we have the interior application, like we call it communication furniture, where we really can adapt to different possibilities. For this project, you can see the first one-to-one prototypes or pieces at the stand here in Hall 12.1 at Mitsubishi and Colossus. So it really goes into this direction, and we have other morphologies for further seating landscapes, imagining sitting there or seeing them at airports, for example, or foyers. We first had our first trip to Dubai as well, so we made this kind of approach, like thinking further into a skyscraper, which is of course difficult with plastics, but there are certain possibilities by self-shading and using wind and ventilation channels to create here a different quality of facade as well. And we have experimental projects like pavilions, where we work with other colleagues together. In Paris, for example, where we're looking forward to use this whole or use the material in a whole as a floor and ceiling to create really new spaces and new impressions. And we were really lucky after a speech. We had our first project from the research to application. We met let's say, the building director of the Deutsche Museum in München. And he said, hey, I might have a first project because we're in the biggest alteration right now of the Deutsche Museum and we need a temporary main entrance. Would you like to come up with a design for this? And as you can see here now, this is the first project now of 3F Studio. A lot of people know maybe this museum. It's one of the biggest. It's really located in the center, in the heart of Munich, on a river island. And normally the main entrance was here in the courtyard. And due to the alteration, they have to close the courtyard and move the temporary main entrance on the border of the river, which has like a really nice positioning and visibility. So it's the largest tech museum in the world, they say. They have 1.5 million visitors almost per year. And this will be then the largest industrial application, 3D printed structure as well, out of a fully recycled material. This really fits well to the temporary approach of this building. And we really show this transformation from research to product. The big thing about it, it's not really like being able to print a piece of a 3D of a facade, but the scale here is really immense. It's like 750 square meters. And if you think 1 square meter takes around 3 to 4 days, you can imagine like how long does it take and how many printers do we need to fulfill this. And this really takes it now really into another stage. And we're really happy about this to get there, because this was really tough in the beginning. We had like 4 months time to do all the certification, of course, because it's a public building. So we first had to see like, okay, how can we, or with whom can we produce those elements? And we were happy to find a partner of Big Rep, the Big Rep 1 machine, to really produce like 1 square meter big panels. So that was the first step, that, okay, it works, we can produce them, but then the hard facts came, fire testing. This was quite interesting. The fire department of Munich came to this test and they were already laughing that this project will stop now because the plastic will burn away really quickly. But yeah, after the test they were pretty quiet and thought, oh, this is a really interesting plastic. And it was really melting mostly, and there was no smoke, almost no smoke. So we got a really good result for the fire testing of the PTG. And the next thing, besides UV resistance, all different U values and G values, and like we had to do the structural testing, of course. And for this, we really built like a whole piece of the facade in the size of 4 meter by 2 meter. And there we really had to like already show all the fixings, how we connected, and did all the structural testing. And we were really, it was pretty tough because we only had this one chance. We didn't have time to make a couple alterations. So, but we passed this test, and now we can really say we can print 3D, or we can install 3D printed facades. So this was for us really a great chance to get from the research project really quickly into the application.
It's not finished yet. All the work we do at the 3F Studio Analyze is based on a specific approach and methods where I come larger into play, because I think 2 criteria are very important in the background with additive manufacturing: resolution and geometrical complexity. But before I explain this in detail, I want to make a categorization into surface and spatial structural morphologies. For one reason, to define a framework, but also to differentiate qualities. In the case of the surface, summarized in functional properties of the facades, but in more like a structural way in the second category, to also focus this in the development of the project and the concepts. I think every larger step in technological advancements brings the possibility to look at existing architectural building solutions from a completely new way, but also developing completely new solutions themselves. To use the full potential, I think it's essential to think in first principles, to really develop an idea of an ideal form, in this case of the facade, looking at the functions like shading, lighting, and insulation, how they can individually be answered or solutions be found in the geometry that can then integrate it together. For that, three parts of the approach is the first one, computation, which gives us the ability to generate, design more complex forms that it would be possible by hand, to simulate them, how well they perform regarding to structural or energy analysis, to then basically find a geometrical result that has more accuracy and could not be computed by a human brain. Connected or then early integrated in the design process, the material and the production method itself then informs not only in the direction of using the full potential of the morphospace of the material and the printing machine, but also to only generate results that can actually be produced. Both that combines, I think, enables an unseen resolution, which not only gives new ideas for architecture solutions in general, but also enable a new view into nature. I think this new view through higher resolution is quite critical, because what we see in planning and constructing today is basically predefined geometrical simplified shapes according to the subtractive methods we use. Additive manufacturing then really opens up a complexity which is not the goal of the design process, but the emergent consequence. And I think that is a strategy like it is in nature, and this objectivation helps to a certain extent to really look more deep into nature, not how the shapes look like, but how the processes behind them actually generate those shapes. This is one example of a diatomon structure. Basically, the intelligence is here constructing with less material through complex geometries, superstructural and load-bearing shell structure, which is porous. And I think it's relevant to bring this intelligence into the future development of architectural solutions for morphological systems and material strategies with high resolution and high geometrical complexity, to actually increase or use the possible increase through the technological advancements that we have at our hands at the moment. I want to explain one aspect of this design process we use with the German Museum as an example, because the self-shading of the facade is the most prominent characteristic of the design as well, which was then also connected to this smooth surface folds that you have seen before. And here, the concept of the architecture basically gave those here blue-marked areas that needed daylight. And in this part of the building, we also wanted to control this. We wanted to basically increase the amplitude, and by that, decreasing the energy input. we do look exactly how on site the sun moves. The animation didn't work, but the next step would then basically be to calculate the optimal angle for the fold according to statistical weather data, then compared to a standard flat facade here, well represented by the blue areas self-shading the facade and also technically, improving the technical performance, but also enabling, I think, a very distinctive aesthetic, which not only from a design standpoint, but from the whole process, really implies the tools and the materials that were used to actually design this. On the second part, I want to focus on work I do and with a larger focus, like said before, on spatial structural morphologies. Basically, the problem here is the same, is limited building material resources. How can you build the same thing or new qualities with less material? And there, out of the research I did about those morphologies, trying to save materials, one project is already built. I'm also a little proud of this, and one of the main actors also is here in the room, because this is a project done by me and artists and the FIT-AG, which there was Bruno Knitschaller mostly responsible for the technical development. The concept and the design for the project actually started years before the actual project came on the table. I met those artists, we understood each other on the level of how to use new technologies in specifically this Gothic church to basically make their connection with the building itself. But then also to find, in this case, the artistical concept, a way of closing up the renovated altar space by relating or covering the window behind it, but also relating to the size of the columns of the Gothic church itself. And as said before, this was the playground for the research about those filigrane structures as a solution to save material and architectural solutions, to test really out the sculptural qualities in this art context. The basic idea here is trabecular bone structure. This was algorithmed in the way of how the density varies to the load differentiation in bone structure, but then here brought into the piece, topologically optimized on the left side, red high loads. The node-based algorithm then generated more structure in areas with higher loads, and this sort of material saving but aesthetically used process went on so far that actually also the surface was informed by this, by carving out little pieces of the structure, even reducing further the material used here. I think the contrast could not be higher. Gothic architects, form finding, and the historic building, but then this new high-tech method. I think here the quality that still holds this together harmonically, I explain in a way of a quality of consequence between the form and the material itself. And comparing this to Gothic architecture, basically, if you see the ornament, you can't take it away, but the structural system of a Gothic church, for instance, would still hold up. Here you can't hold it away. By combining this visual and constructive aesthetic so tightly, I think this is actually a new quality that is, from my view, also provoking a question how we do architecture today, because with additive manufacturing, you can have very contrasting ideas and contents, but they fit together on quite a deep level. As example, that this is a morphological system, pardon me. I want to explain a little bit more the material strategy behind this, because that was quite critical to actually produce the piece at all in 60 segments, but only 400 kilogram super light weight. The idea was to print, of course, but to metalize the structure. So there was really the idea of making this a very long-lasting sculpture. We had approached different companies, WEM processes, but then together with Bruno Knitschala, we came the idea to actually spray this with aluminium bronze with a wire arc process. So then Bruno Knitschala did a lot of testings how this then actually really was resilient enough to hold all of this together. So quite amazing technical development behind all this, as well as the enormous mega puzzle that came out of this. I don't know if it was fun, but I think that there was a huge hands-on process that is quite astonishing. Those pieces were partly put together in stripes, then again sprayed with aluminium for an even surface. Here, an impression of the piece that was put in place to put the final gold metal pigment coloring, which is shown here, and you're all invited to see this. It's 60 kilometers, 1 kilometer east from Munich. One part of the project that I want to make now to an outlook was the idea of actually bringing the morphological system also into the shell of the rod system itself by having a porous surface where you have smaller pores that are closed off in the spraying process, but then aesthetically used it in parts where they would still remain open. To show that this is an example, system that can also be transferred to different materials. I only brought 2 pictures for this because there is a lot of questions still to be answered. Concrete, lightweight concrete in this case, there is an issue of tension which I need to look into. But this was developed as a demonstrator for the TU Munich for the chair of wood construction with Claudius Hinke. And besides the inner core that you see here, which is a section out of a column, you see outer surfaces, which I think also connected with those filigrane qualities go quite well. I want to show one last concept that didn't make it into printing, into realization yet. It's a fibrous morphology based on a water sponge. Basically, algorithm was the way of how the strands of the silicium dioxide are directly oriented along the stress flow of the actual cell structure. So this was then applied again on a basis like this column-shaped volume in the church on a topologically optimized sort of domino 3 slabs just as a base to really then analyze the stress flows spatially. In the animation again does not work, but I think you understand what this is about, tension and pressure. That is very unfortunate because you should see red lines very nicely generating themselves around those stress lines, making the structure. No. Well, this happens. In a final step, this was digitally thickened. And with the final resolution of this concept, there is a smaller cutout of one column. basically the strands would be 2 to 6 millimeter in diameter. Again, this could be from concrete. This could be the same technique for the church. This is a concept. I hope I gave enough impulses, and I want to thank you.
Thank you. Okay, this was an impact at the end.
Yeah.
Yeah. Questions? Questions? There's a microphone.
We have to say one more thing. Like, if you want to see like a piece of the Deutsche Museum facade or facade, it's located at the BASF fair stand here in Hall 12 as well.
Yeah.
Like 2 meter by 1 meter. You can take a look at that.
12, first floor.
Yeah.
Questions? I obviously do have questions. Obviously. Fire you talked about, okay. About your Munich facade, huh? The museum, 3 months to plan it. The tires are interlocking themselves, so there's no substructure behind the tiles, or is there a substructure in the
There's
tile?
substructure behind it.
Okay,
Yeah.
So the tiles are as tile stable,
Yes.
they don't have to interlock.
Yeah.
Okay. And then obviously you compare it to a normal facade. Well, is it transparent?
Not yet.
Not yet. Okay. Can you imagine it's transparent?
Yeah,
Where's your 3D printer whisperer? Can he make it transparent? Where is he?
Here.
So he had pieces of glass. A question of resolution, huh? You have to get to a nanoscale to get this seriously done. And finally, water. Any experience with water?
Yes.
Yes.
Yeah.
What? Yes.
There was some water, especially in the long-term prototype, where we had this closed cells.
Yeah,
but now we changed
yeah?
the geometry. Yeah, humidity.
You need to drain it.
Yes, and then now for the Deutsche Museum's facade, we did some climate testing, and it passed this as well, because we changed the geometry. But this was like a big aspect in the beginning.
I absolutely can imagine. When you get to say to the building products, which are to be compared with normal products.
Yeah, it's tough.
That's tough. Yeah, I like it as an experiment because then say it's limited time, and after 5 years you just take it off, and then it's.
We'll see.
That's a good start. Any question? Yes, microphone.
Hi, thanks for the presentation. For the facade, what was the insulation strategy and what U value did you achieve?
With the prototype, we achieved a U value around 1.6, and the strategy was to use air as insulation. If it doesn't move, it has quite a good insulation value. So this was the starting point, and that's why we choose as well the FDM process, because we could really print like enclosed air cells. This was with the powder printing not possible, besides using a transparent material.
Thank you.
Clear? Okay. Any more questions? Yeah, there's another one.
Thank you for your presentation. The good things about your presentation was your experience and new material in the construction. From the morning we hear about the concrete, the steel, sand, but PET is very new in the construction, as I know. My question is PET also, in your experiences, could working on a structure panel? Intention in other aspects that is needed. Thank you.
The first tests were really good with it, because through the FDM, like, you have this really good layer bonding because it gets melted together. So this first test for tension compression was easy, let's say. It's not a very soft material or plastic. So, but the tension and Biegung, bending were quite good results already. So especially we already only used like 6 centimeter thick panels. It was really good results. So I think there already have been some PETG facades around, but I think in this way we can really use the geometry much better than just having a flat panel.
Yeah.
And due to the double curvature of the waves, it gets really, really stable. It's really...
What's the weight of one of these panels?
13 kilograms per
13
square
kilograms, so
meters.
it's not nothing.
No, it's not really nothing.
Okay. No more questions. Thank you. Applause.
Thank you.